So right now we're going to look at algorithms that operate on more complicated values. So I'm looking at section 7.4, and 7.4 discusses searching. And you're going to see a couple of different searching algorithms, and this video is going to focus on what is called a sequential search. And it's the one that pretty much is always going to work. Other algorithms get better performance by assuming something about the data. And the idea here for the searching algorithm is that we have a list of values of some sort. So let's imagine we've got a list of numbers. So each number might be 2 bytes long, right? So maybe we've got a width here of 2 bytes. And that's stored in an array. So we might call this array numbers. And so we have at index 0, we have the first number. At index 1, we have the second number, and so on. And this type of algorithm, you could imagine it working for n different numbers, right? So which means you would have indexes going from 0 to n minus 1 at the end, right? So this would be at index n minus 2, you have another number, and so on. And the searching problem is this idea of how, if we have a list of numbers, can we answer the question, is there a 3? So we can look back and we can say yes or no. And we could also answer kind of that follow-up question, which is, where is it? So if there is a 3, we would like to be able to determine its index. If there isn't a 3, then maybe we could, if we ask you where it is, you could say something to indicate nowhere, like a -1, or a like FFF. So you have maybe some special index to indicate that it's missing. So that's a kind of a related question. So if somewhere in this array, at some index, let's say I, we have the value 3, then we would expect this thing to come back and say, oh, yes, there is a 3, and it's at index I. Now, if we were to ask it, is there maybe a 7, we go through and there are no 7s, so maybe we say false, and its maybe index is, we leave it garbage, or we set it to -1 or something. What we could, so this is kind of this idea, and what we need to do is take this process that we would use to search for a number, and we need to express that as an algorithm. And I think the process that we're talking about for sequential search is the obvious one that we know. I'm going to make a little arrow for myself with a piece of paper so I can move it around. You're going to start at position 0 and check if it's there, and if it's not, you're going to increment down to position 1 and check if it's there, and if it's not, you try position 2, 3, 4, etc. The very first time you find a match, you can stop, because you found a 3 and you know what its index is. There's no need to go down anymore. So this is a loop which is a little bit odd, because suppose that you're looking for a 7. You compare the first one, is that a 7? No. And that one isn't a 7 either. And you keep scrolling down the array, never finding a 7. You hit the end and you haven't found a 7, but you need to stop once you've processed n minus 1, or once you've processed n values, you need to stop. So we have 2 exit conditions. If we find the thing that we're looking for, then we want to exit. Equivalently, if we don't find the thing that we're looking for, we also want to exit. So there's kind of 2 conditions that would cause us to want to exit. So let's think about how we would do this in pseudocode. We're doing a counting-based loop here, so we know the pattern, right? So we're going to set. They use the word position in your book, so I'll follow along, even though I like the word index better. So we're going to set position to be a 0, right? So this is by the way, this is the sequential search algorithm. Some people call this a linear search algorithm because that is a way to describe how long it takes to do the search. So this is a linear or a sequential search algorithm. We are going to set position to 0, and we haven't found it yet. What we're going to do is we're going to keep a true or false variable to indicate whether or not we've found it. So we're going to set found to the value false. Usually for Boolean variables, you only need 1 bit, but computers always deal with bytes. So for Boolean variables, 0 is false and non-zero is true. So any value other than all zeros would be interpreted as true, and found is set to 0 or false here. So now we're going to have a loop. So while. So the condition of our loop, remember we've got these two things. Either we find what we're looking for, or we've gone past the end. So there's 2 reasons we might want to end this loop. So in order to express that in the condition of this while loop, we're going to need to use the logical AND operator to combine those 2 conditions. So we're going to keep repeating as long as we haven't found it and we haven't gone past the end. All right, so those both have to be true. So while position is less than n, right? In our case, in the book it's 10. I'll just write n. While position is less than n, that's equivalent to saying we're not at the end. Right? We're not at the end yet. So while position is less than n, and also, if both are true, found is false. So you might want to put these in parentheses if you're not sure about the order of operations. So for instance, so found is a Boolean, position less than n and found is a Boolean as well. But what you really want to do is you want to check whether found is false. So if found is false, this expression would be true. Right? So this has the opposite truth value of found. Right? So if found is false, this is true. If found is true, this is false. Right? So this basically means you haven't found it. And this means you haven't gone past the end. So while we haven't gone past the end, and also we haven't found it, we're going to keep doing some stuff. So this is a slightly more complex condition than you've seen before. And, you know, I think people sometimes have a very hard time dealing with these, I think they're called conjunctions, these logical connections, and, or, and also exclusive or, and sometimes not. So these are different operations which take some true, false values A and B and then return a new one. So A or B, A and B. A exclusive or B is what we usually mean in English. So this is A or B or both, and this is A or B but not both. And then not A. So not A takes whatever the truth value of A and returns the opposite. So if A is true, this is false. I guess it would be a fun challenge to see if you could rewrite this condition to be maybe 1 word shorter. So this is the idea of the while loop, and inside that while loop we're going to either set found to be true, or we're going to increment the position. So as we're going through, we're going to check. So if we found it, then that would mean that the value at that position is equal to the thing that we're looking for. All right? So we're going to imagine that there's some value being fed into this called search item. And so this is given. Remember, from problem solving, you always want to know what you're given, right? So we're doing a sequential search for search item. So as we're going through, if numbers position. Remember, position is, as we do this counting, position is going to cycle down through. And so numbers position accesses this value. So numbers position is giving you access to the value indicated by position. Right? So if numbers position is equal to search item, and I'm going to use two equal signs to indicate that this isn't an assignment. I use arrows for assignment anyway, so it doesn't matter. This is comparing values. If it equals search item, then what I'm going to do is I'm going to set found to be true. Otherwise, so this is our selection, right? So else, this means that we haven't found it yet, right? Well, if we haven't found it yet, then we're going to just advance to the next item, right? So and if we haven't found it, I'm going to set position. I'll set it to get position +1. So if we've done it, and then of course it'll loop back, right? And so when we're done, we could print found position. So from this you could answer some questions. What is position if you don't find it? So if you don't find it in the array, position is going to be n, equal to n, the size of the array. If that's not obvious, we could trace through the code. Maybe that would be a fun thing to do. So let's put the code right there. Let's imagine we've got an array of 10 numbers. Let me see if there's one in the book I can use. Great. So the book has an example with an array that has 6 values. So they actually introduce another concept in the book. Let me point out real quickly. You can have an array of values here. And so let's call this thing numbers. And sometimes you don't know how big the array is going to be when you're writing your program. But in order to allocate the space, you need to know how much to allocate up front. So you might allocate an array of lengths max, some max length. And so you have indexes that go from 0, 1, 2, all the way to max laying, whatever, -1. And that would be the last position. However, when you're searching, you might only want to use a part from the beginning of the array. So maybe you have, you're just looking for an item in this little subarray of length 6. The idea here is there can be stuff that follows after, and you just don't really care about it. You kind of waste a little bit of space. Later, you might learn how to, there's really complicated things that your operating system can do to allow you to guess how much space you need and then later increase it if you have to. But we're not going to talk about that now. In your simple programs, you would just have some max length. So like Pac-Man, maybe you can only handle up to 255 values before things go crazy, right? So you just have to guess what the maximum is. So here we can do that. 1, 2, 3, 4, 5. So we can imagine that we're just using the first 6 position, whereas our algorithm can handle anything up to max length. I just wanted to point that out. I've kind of done that same thing with strings before, because often you need to know what the capacity of things are. So we've got an array of numbers, and let's pop in some values there. Just copying off of your book: 60, 75, 95, 80, 65, and 90. And down here, who cares? We aren't looking at it. All right, simple idea. So if we're not using the whole array, we can use some other value to indicate what the length of the array is. I called this n. Your book calls it length. So when I was writing my pseudocode, you would be given not only the search item, but you probably also want to be given n, and maybe even the address of numbers. So sometimes it doesn't hurt to think about what you need in order to do this calculation. So this is an array, an unsorted array of numbers. Let's imagine that this has been read in and it's stored in memory somewhere. Your book has code to read in an array of values, but I think I've already gone over that pseudocode in another video with you. So we're going to trace through this algorithm with this array. So it looks like the variables are position, found, search item, and numbers. I don't need to write those down. Okay, so we've got position and found. This is position. All right, so this is position. So found is false, right? And position is, I'll write it twice. I'll write it as a number and as the arrow. So position, if we trace through this algorithm, is, let me get another arrow. This is the current line of the algorithm that we're executing. So position gets set to 0, and found gets set to false. We're going to check this condition. So in order to check that condition, we want to know is position less than n? And we also want to know if found is false, right? And then of course the both, right? So we'll be able to figure that out. So as we go, I'll try to keep track of those things. So here we got to check, is position less than n? So position is 0, n, or the length, is 6 for this problem, right? So is 0 less than 6? That is true. And is found equal to false? Yes, indeed, found is equal to false, so that is true. Right? So since both of those are true, we're going to go into the loop. Right? So now we're in the loop. We're going to check whether numbers position, so by the way, position here is 0. We're going to check if numbers position is equal to search item. Right? So we're checking, I didn't say what we're searching for, let's imagine that we are looking for, let me see what the book looks for. Let's imagine that we're searching for 76. So let me just do S for the search item, and we're looking for 76. So our position is 0. In numbers position is 60, and is 60 equal to 76? No. So we don't do that, right? So only if that was true would we do this. It's not true, so we're going to come down here to the else. And what that is we set position equal to position plus 1. So position becomes equal to 1, which is down here. And then we go back up to the top of the loop. We check our condition. Is position less than n? Is 1 less than 6? That's true again. Is found false? That it is still false, so that's true. And we come down here. And if numbers position is equal to search item, so numbers position is 75, and 75 does not equal 76, so we don't do that. We go down here, else we set position equal to position plus 1. Position is less than n, found is false, position here is 2. So is position is 95 equal to the search item? That's false, so we go down here. We set position equal to position plus 1. Up here, 3 is less than 6, and found is still false. Numbers, so position is 3. Numbers 3 is 80. 80 does not equal 76, so we do the else. I hope we see what's going to happen here. We set position equal to position plus 1. We come up here. Is 4 less than n? Yes. Is found false? That's also true. If numbers position, numbers 4, is equal to the search item, is that equal to 76? No, so we go down here to the else. We set position equal to position plus 1. We continue the loop. Is position less than n? That's true. Is found false? That's true. So we come in here. We check if numbers position is equal to search item. That's 90. 90 doesn't equal 76. So we skip over that block and we do the else. We set position to 6. We come up here. Is position less than n? Position's down here, which is not less than n. So that's actually false. Found is still equal to false, but we don't care. Position is less than n, and since any one of those two is false, we're done with the loop. Right? So found is false, and position is 6. So what this is going to produce is output is it's going to print false and 6. I'm sorry, false and 6. Right? So let's try this again, but instead of searching for 76, let's search for a different value. So I'm going to try to get creative with my paper. Is this going to work? Now I just need some tape, right? Okay, so let's try this again. We are going to be checking whether the position is less than n. We're going to be checking whether we found it. So is found equal to false? We want to be checking the what the value of found is, and position. And the length of the array, and the search item. Right. So here we go. So we're tracing through this whole thing again. We start off, we go through, we set position to 0. We set position to 0. We set found to false. And we check our condition is n, by the way, is 6. And our search item, for now, I want to search for the number 75. Right? So position is 0, n is 6. Okay, so is position less than n? That is true. 0 is less than 6. And found, is found equal false? It is, so that's true. So we're going to go into this loop. Positions here, by the way. And so now we were looking if numbers position equals to search item. So 60, is 60 equal to 75? That's not true. So we're going to skip this. We're going to go to the else. We're going to set position equal to position plus 1 and continue the loop. Is position less than n? 1 is less than 6, that's true. Is found equal to false? It is equal to false, that's true. Position's down here at 1 now, right? So now we're going to say if numbers position is equal to search item. So the search item was 75, numbers position is also 75. So that's true, so we're going to execute this piece of code. We're going to set found equal to true. And we don't do the else part, we come back up here to while. So notice we didn't increment position, it's still a 1. We come up here to the while part and we check. Is position less than n? Is 1 less than 6? That's still true. And is found equal to false? Well, found is true, and true does not equal to false, so this is false. And because of this and up here, they both have to be true. And since they're both, one of them isn't true, we're going to jump out. And we're going to print found, which is true, and position, which is 1. So we're going to print out true and 1, indicating that yes, we did find a 75, and we found it at position 1 of the array, which is correct. So hope that was good fun. And that is the sequential searching algorithm. You can actually improve on this a little bit if you know more about the array. For instance, if we knew that the array was sorted. So let's imagine we have a sorted version of numbers, and its length, so I'm going to use n is 6, and numbers has the values at position 0, 1, 2, let me put the numbers on the other side. 0, 1, 2, 3, 4, 5. It's got values 60, 65, 75, 80, 90, and 95. There we go. So the important thing here is each number is bigger than the one that follows it, right? So if this value here is called numbers, numbers I is less than or equal to numbers I plus 1. It always is, right? So if I is 0, you have 60 is less than 65. At 2, you have 75 is less than 80. At 1, you have 65 is less than 75. So no matter what, this condition is true, that means you're sorted. You have a sorted array. And you can actually exploit that piece of information because if you're searching through a sorted array, you move down. Let's imagine that I am, maybe I'm searching for the number, computer went blank. Let's say I'm searching for the number 73, right? So I'm searching through a sorted array, and I see that the array has this value 60. Well, 60 doesn't equal 73, so I go down here to 65. 65 doesn't equal 73, and now I look and I see 75. And 75 is bigger than 73. So if I ever encounter a number that's bigger than 73, I can stop and I can say, nope, it's not in the array. So that means that I don't ever have to look at any of those values if I know that the array is sorted. So in some situations, when you know something about your array, like the fact that it's sorted, you can have an algorithm which is sometimes faster. Now, you can actually quantify how much faster. If your item is actually in the array somewhere, then the most likely position for it to be, like if you were to do it 1,000 times, on average you're going to end up finding it around halfway through the array. So every single number is equally likely to be less than what you're looking for and equally likely to be greater than what you're looking for. So since any given number is equally likely to be greater than or less than what you're looking for, the expected position is going to be right in the middle of your array. And there's much more rigorous math that you can do that. So on average, this algorithm on sorted values, if you know that they're always sorted, and if you stop as soon as you find one greater than what you're looking for, you can do something which is maybe twice as fast, so 2 times faster, if the thing that you're looking for is in your array. Now, if the thing you're looking for isn't in your array, the analysis, it's about the same. It's pretty much the same. You have to include, it could be in between any pair of values, or it could be way out in the ends, right? So yeah, but basically you can get about 2 times faster if you know that your stuff is sorted using a sequential search. And I don't know if your book discusses that. Programs use index rather than position. Okay. So we can do much better than 2 times faster, actually. So it's possible to search through it's possible to search through arrays at a sorted array at a speed which is as close, pretty darn close to constant speed. Basically, it's on the order of the number of digits that you would use to specify the size of the array. So if I have 1,000 elements versus 1,000,000 elements, then this guy, so searching through 1,000,000 elements would take me only 50% longer than searching through 1,000, right? So even though this is 1,000 times bigger, it might only take me 4 times as long, right? And that's huge, right? So versus a sequential search, I might have to do 500,000 comparisons on the order of 500,000 comparisons. There's an algorithm which could do that on the order of maybe 6 or 7 comparisons. So compare that 500,000 to 6 or 7. There's an algorithm which is about that much faster. We call this linear speed because the time that the algorithm takes is proportionate to n, and we call this logarithmic speed because the amount of time the algorithm takes is proportionate to the number of digits it takes to write the number down, right? So a linear search might take 1/2 of a million, which is still 500,000, whereas a logarithmic search takes the number of digits in a million, which is like 6 or 7. And you can see that this gets, it not only is much faster, but for the bigger the numbers get, the more fast it is. Right? So Yeah. Usually we use a log base too. Right? So if you have, you know, if you have a sorted list of numbers, you can do something called a binary search, and I'll do that in the next video.